Welcome everyone. I see a lot of young people, which is great. We just heard an excellent talk by Harley Katz. He's currently at the University of Chicago, and he made a choice to be in astrophysics after spending a couple of years outside astrophysics. So I think it's at least evidence that what you are doing is interesting, right? Where is Harley? Yeah? And we will hear more from him about the nebular continuum and particular stellar populations at high redshift. So apparently the data from the Webb telescope is quite intriguing and needs interpretation. That's what we theorists are for. So thank you, Harley. After that, we'll hear from Oliver Muller from Switzerland. Where is Oliver?
Here.
Oh, here. And yeah, it's colder than here, isn't it? Yeah. Actually, he's also at the University of Cambridge, right? And he will talk about direct evidence of nuclear star cluster formation in dwarf galaxies. And then we'll hear from Ivana Barisic from UC Davis, over there. And Ivana will tell us about NSA 3D, dissecting galaxies at redshift 1 with high spatial and spectral resolution. Now we call these galaxies low redshift galaxies. It used to be 30 years ago they were the highest redshift. Cristhian Garcia-Quintero from the CFA will tell us about Baryon Acoustic Oscillation measurements from DESI DR2 and cosmological implications. Many of us theorists are really worried about that because it would be difficult to explain why the dark energy had an equation of state of a phantom scalar field like -1.4, which is the latest. And also it worked on the Hubble timescale, so we will have a lot of questions for Cristhian when he speaks. Harley, please take it away.
Well, thank you. Apologies to everyone who was here for the last hour. You're only stuck with me for 10 more minutes. I'm going to talk a little bit about a project that we've been doing more on the observational side of Webb, which I think has actually been extremely exciting over the last 2 years. So for those of you that don't stare at spectra every day, I'm just going to break down what the spectrum of a galaxy is. On the x-axis is wavelength, and on the y-axis is solar luminosities per unit angstrom. You have a blue component here, and that is your standard stellar continuum, so all of the continuum radiation coming out of stars. But of course, that's not the only thing that emits in a galaxy. You have your nebular emission lines. Many of these you'll identify, your recombination lines like H alpha, H beta, your collisionally excited lines like oxygen 3, nitrogen 2, et cetera. And typically, we think of a spectrum as basically stellar continuum plus nebular emission lines. But there's another component that we often rarely consider, and that's the nebular continuum. And it's a combination of 3 processes. It's free emission, free bound emission, and 2-photon emission. And these 3 processes have very distinct shapes. You have a smoothly rising continuum, sort of this sawtooth shape, and then something that comes up very close to Lyman alpha and then plummets just before. Okay? And so just keep those shapes in mind. And with James Webb Space Telescope at very high redshift, redshift 6 and above, we're typically probing sort of some of the rest frame UV and rest frame optical emission. So one thing to note is that when a galaxy undergoes a very strong burst of star formation, the nebular continuum all of a sudden becomes visible. And so here I'm just showing you results of simple simulations from toy models. Here you're looking at a very smooth star formation rate, a very sort of cyclic but bursty star formation rate, and an extremely bursty star formation rate. The cyan line gives you the stellar continuum, and the magenta line gives you the sum of the nebular continuum. And what you can see is that for smooth star formation rates, the nebular continuum is completely subdominant to the stellar continuum. But as you go to burstier and burstier star formation modes, all of a sudden the emission from the gas is popping up above the stellar continuum. And for the most part, that's dominant in the sort of rest frame optical and the near infrared, and it tends to still be subdominant even for very bursty star formation rates in the rest frame UV. And so you can put this in sort of a more formal context. You can take all of your standard stellar population synthesis models, Starburst 99, binary stellar evolution, Charlot and Brugeral, FSPS. You can just run them through a photoionization code like Cloudy, and you can just calculate what fraction of the observed continuum radiation is coming from the nebula versus from the total, okay? And so on the x-axis is stellar age. As the massive stars die off, they produce fewer ionizing photons, which means the nebular continuum comes down. So all models you see drop at large stellar stellar ages. And depending on the exact details of the model, at very young stellar ages, at rest frame 3640, so this is in the optical, what you see is that the nebular continuum can dominate up to 75% of the total light. And in the rest frame UV, depending on sort of the stars that are in your SPS model, it's typically well below half, around 25–30%, okay? And so this is neat. You can see that the nebular continuum does impact the rest frame UV and the rest frame optical. And so for very certain stellar population synthesis models with normal star formation histories, you can just calculate the change in brightness due to the addition of the nebular continuum. And here's the delta MUV. And you can see that most galaxies of around a change of 0.25 magnitudes, which isn't a huge amount, but still not nothing, whereas some of them can increase by 0.8 magnitudes. And I should mention that this effect is ignored by pretty much all models and all simulations that compare to high redshift JWST observations. And so it's an important effect, but it's not dominant. And you can ask yourself, what do I have to do to the stellar population synthesis models in order to increase the effect of the nebular continuum? So there's two ways you can do it. The first scenario is you can modify the initial mass function of the stars. So what you can do is you can change the upper mass slope, which gives you a higher proportion of high mass stars, but you can keep the upper mass limit fixed. And so if we just compare models with different upper mass slopes going from very steep, saltpeter to much more flat, you can see that the impact of the nebular continuum is rising in both the UV and in the optical. And of course, as you go to old stellar ages, it plummets again. And you can look at the change in UV luminosity. Again, at young ages, you get a huge burst in UV luminosity by more than a factor of 10 if you go to these extremely flat slopes. But this UV luminosity increase is due to changing the IMF slope. It's not due to the substantial increase in the nebular continuum. So I'm not going to talk about a change in IMF any further. Another thing you could do is you can allow for hotter and more massive stars. So here on the x-axis, you have stellar temperature. So this is the photospheric temperature going from around 40,000 Kelvin to around 100,000 Kelvin. And depending on the gas density, what you find is that if you just focus on the solid lines, which is the rest frame UV, instead of having sort of a 20% contribution from the nebular continuum, as you go to very hot stars around 100,000 Kelvin, you see that your spectrum is completely dominated by gas emission and not stellar emission. In fact, around 90% of the total UV emission you see in the rest frame UV is coming from the gas and not the stellar continuum. And again, if you just compare the ratio of 1500 angstrom luminosity to a typical O star, you see a very strong increase with effective temperature. And what this is an increase in the gas emission, not an increase into the brightness of the star itself. And so this scenario actually is extremely interesting. And there's three key observational diagnostics of hot, massive stars, okay? So the first one is that the UV slopes become extremely flat. So if you look at a typical stellar population, again on the x-axis is age and y-axis is UV slope, the intrinsic stellar population has a slope of around -3.2, but as soon as you allow for gas emission, it comes up to around -2.5 because it's the free bound emission is flattening out your UV slope. However, if you allow for hot massive stars, again, the intrinsic is sort of well below -3, but all of a sudden you can start reaching these UV slopes of around -2 to -1. So hot massive stars look redder in the UV than less massive stars. So that's the first observational diagnostic. The second one is the number of ionizing photons you're producing per unit UV luminosity is increasing. So on the x-axis is a parameter we call psi-ion, which is essentially the ionizing photon count divided by the UV luminosity. And you can see for a typical stellar population for very young ages, it peaks at around 26. If you allow for hotter stars, it gets to around 27. So it gets very, very, very high. However, if you go and try and measure the psi-ion, it pretty much asymptotes at 26. You can actually never measure a psi-ion higher than the typical value for a stellar population. And the reason why is because you're dividing the ionizing photon production by the nebular continuum. So you're essentially dividing the same photons by themselves, which is why you see this asymptote. The third diagnostic is you start to see a downturn near Lyman alpha, and this is effect of the two photon continuum popping up above the stellar continuum. So it looks like a damped Lyman alpha system. And so you can try to parameterize that with a DLA column density. And so as you go to higher and higher stellar temperatures, you see a stronger and stronger downturn, and you can even approach DLA column densities of around 10 to the 23. And so why are we considering this? Well, about 2 years ago, we stumbled upon an extremely peculiar redshift 6 object. And so first order, it's a booming Lyman alpha emitter, extremely strong equivalent emission lines. And you see the Balmer jump feature here, which is a clear signature that the gas emission is very bright. And you can go to your favorite photoionization model, like cloudy, and you can just assume pretty normal stellar populations. And for the most part, you can fit the strengths of these emission lines, you can fit the Balmer jump, you can fit the Lyman alpha. And overall, it does a pretty good job. The only annoying pesky feature here is you see this very strong downturn in the UV, okay? So you see that it pretty much fits all the way along the way, except right near Lyman alpha. And so you have to figure out a way to get a strong downturn in the UV while also having a Lyman alpha escape fraction of 30%. And so what you need is, if you try to fit the DLA column density to match this, you need a value just above 10 to the 23, which would be one of the record holders for the highest DLA column density ever observed. But this DLA column would have to be like Swiss cheese and allow 30% of the ionizing photons to escape. So it's possible, but it's extremely contrived. So another thing you can do is you can measure the temperature of this ISM based on the oxygen 34363 line, and you get a value of around 18,000 Kelvin. And you can ask, what is the shape of the nebular continuum at 18,000 Kelvin? And that's this magenta line. So it's not a fit to the galaxy. It's just what you expect from a nebular continuum of around 18,000 Kelvin. And it's almost a perfect match to this entire spectrum. And I don't think that's a remarkable coincidence. I think this galaxy is entirely dominated by gas emission and not stellar continuum. And you can ask, what does this spectrum have to look like in order to not only match the shape of the continuum, but also the emission lines? And what we find is that it kind of looks like something like this. It's a black body that has a temperature of around 10 to the 5 Kelvin, okay? But there seems to be some sort of atmosphere blocking the helium-2 ionizing photons. And the reason why we know this is because the helium-2 1640 line is not super strong in this galaxy. You can compare that to models of individual population 3 stars. What I really mean here is just low metallicity, massive hot stars. You can look at helium strip stars. You can look at Wolf-Rayet stars. And indeed, you find that these sort of low metallicity, very massive stars and Wolf-Rayet stars are a pretty good fit to the expected ionizing spectrum of this galaxy. So what we really think this object is, it's a galaxy that's hosting either 40,000 Wolf-Rayet stars or around 10,000 stars that are about 100,000 Kelvin. And this would imply an extremely top-heavy initial mass function. And so, okay, maybe this is just one object, maybe it's just unique, maybe it is one of these Swiss cheese DLAs. But as it turns out, over the past 2 years, we found 3 more. You can see the spectrum here, all have this booming Lyman alpha emission. They have almost the exact same DLA column density and the Balmer jump. And so it's kind of one of these interesting scenarios where multiple galaxies at high redshift are now popping up that have the exact same features. And I think we need to strongly consider the idea that the stellar populations, at least in some galaxies at high redshift, are a bit different from what we have at low Z. So thank you.
When we theoretically predicted 25 years ago with Walker-Brom and Dwarf-Kudrytsky the spectra of population 3 stars, we found that above tens of solar masses, the temperature should always be around 100,000. So that is a generic prediction of population 3 stars.
Yes.
Except the other thing is, of course, you might ask, do they have winds? But they don't if they don't have metals. So do you have any information about the metallicity of these guys? Yeah, we know the metallicity. So I want to make it very clear, I'm not claiming that these objects are population 3 stars. You see the booming oxygen lines here. You see oxygen 2, you see neon. These are not population 3 stars, but what we think is the underlying SED looks very similar to these population 3 stars. The metallicity of this object is around 5–10% solar, and it's similar among the other ones as well. Are you saying that there are pockets of low metallicity within the galaxy? Or? Yeah, so obviously keep in mind we're measuring the gas phase metallicity, not the stellar metallicity. So the stellar metallicity might be lower, and if the gas densities are high enough, you can rapidly cool the IS. Like you can basically illuminate the immediate ejecta from the slightly more massive stars. It could be something like that. Could be something like a Wolf-Rayet stellar population. It could even be a black hole that's just mimicking the SED of one of these 100,000 Kelvin black body with an atmosphere-like feature. So it could be anything of the above. We don't see any strong evidence for a black hole. We don't see any of the higher ionization emission lines or anything like that. So we do think it's stellar. The lines aren't broad, so there's clearly no sort of fast-moving gas. But yeah, beyond that, we have no idea what this is, other than we have constraints on the SED.
just referring to this table here, you have some variation in the H-alpha equivalent widths.
Yeah.
What drives the variation in the H? I mean, if you were really totally continuum dominated, would you saturate to a particular value of the H-alpha equivalent width?
Yeah, so the
Or is
H...
there something that allows that to move?
No, that's right. So the H-alpha equivalent width is obviously sensitive to the exact details of the nebula. So we have I can show you a plot afterwards where you can see the variations of that. But I think one thing to consider is, what I mean by completely nebular dominated is nebular dominated up here. There has to be older stars.
No, that's fine.
Yeah.
I don't mind that there, I'm just asking, sort of, is there a saturated value of the H-alpha equivalent width?
Yeah, it's really high. It's like well above the numbers here. But again, for one, as you can see, the continuum down here is uncertain. But also, there's got to be some older stars contributing in this regime, or else the metals wouldn't be there.
Any other questions? Yes, please.
Yeah, apart from the hot star, have you tried the faster rotating stars, which also will be a very hot star?
So we haven't exhausted every possible SED. We looked primarily at these like individual POP3 models, which again, we're just assuming there's very few, as you know, atmospheres calculations at low metallicity. So we're assuming these are sort of representative of very low metallicity. We looked at like a million different Wolf-Rayet models, stripped helium stars as well. So we've kind of exhausted most things that are hot, but certainly if there's others, we're happy to take a look.
Yes.
And the question, like, it's more in the line of what Avi has been asking. If you think about not about pockets of low metallicity gas, but in return, like basically, when you see the lines, when you see all three lines, they might come. If the medium is not well mixed, you'll have lines, oxygen lines coming from metal enriched medium, while there will be still a lot of not metal enriched medium that you just won't see. But you know, they might create this integrated spectrum that is very hard to interpret in terms of ligations.
Yeah, that's a good question. I think, so if the idea is that you have like a metal-free pocket with the hot stars and like a metal-enriched pocket with like a normal POP2 stellar population, I think that's one way to interpret this, but just keep in mind two things. So for one, the oxygen 3 equivalent widths here are like through the roof. I mean, these are some of the highest O3 equivalent widths we've actually detected at these redshifts. I mean, you're talking like nearly 3,500 angstroms. And so whatever is, like, you have to have an extremely young stellar population to do that. The source is not spatially resolved, or at least it's very marginally spatially resolved, but the emitting region probably isn't, so it's extremely compact. There's almost certainly a mix, like it's not one star, right? There's almost certainly pockets of different metallicity in these galaxies, and this is actually something we discussed an hour ago about how to interpret it in that case, but there's just, because of this feature right here, there's just not a lot of room to hide population 2 stars, because as soon as you put POP2, they don't produce a lot of ionizing photons, and they produce a lot of stellar continuum right here. So you basically has to be a 1-to-1 relation in mass. You can't have more than that, or else you wipe out that feature.
Well, I guess the bottom line is the Webb telescope was worth the money.
Yeah.
That's something that's think harder.
Yeah, that's right.
So, which is the microphone? Okay. Okay. Okay, perfect. Okay, can you hear me? Perfect. And let's share that. So, great, it's an absolute pleasure to be here. I try to not hide so that people here also can see me. It's the first time I give a talk where there are 2 floors I'm speaking to. And as the previous speaker, I also, before I hold this position, I was working as a data scientist at one of the fan companies. So if some of the students want to talk about this experience, then please come and speak to me. Also, please come to speak to me about my science. But yeah, I first announced that I would talk about cosmic ballet, which I think is a huge challenge for cold dark matter cosmology. But apparently I'm giving a seminar tomorrow at the Brett room. I don't know where that is, but so if you want to hear why I think dwarf galaxies are a problem for dark matter, please come and see my talk tomorrow. So today I'm going to talk about something else, which is also timely, about direct evidence of the formation of nuclear star clusters in dwarf galaxies. And it's timely because it gets published next week in Nature. So I think it's a great opportunity to talk about a little bit about that. So what are nuclear star clusters? Nuclear star clusters are the densest stellar objects in the universe. They can contain the mass of whole galaxies, of dwarf galaxies at least, in just a few parsecs. So typically they have masses of 10 to the power of 5 to 10 to the power of 8, and this mass is basically locked within 10, 20-ish parsec. So they are super dense. And they are basically found in all types of galaxies, giant galaxies, dwarf galaxies, ellipticals, spiral galaxies. But they are preferred to be found at intermediate mass galaxies with stellar masses of 10 to the power of 9. So at the mass of the Large Magellanic Cloud, for example. There are two competing formation scenarios for the formation of nuclear star cluster. The one scenario is the in situ scenario, where basically you have gas which falls into the center of the galaxy, and this gas starts to form stars and starts to form this nuclear star cluster. These nuclear star clusters, which are formed from the gas, they basically follow the star formation history of the galaxy. So they will have similar stellar properties as the surrounding galaxy. There's another scenario, which is a migration scenario. So instead of having gas falling in and forming these stars, a galaxy early in its evolution basically forms globular clusters. So that's also stellar compact objects, but just not in the center. These are formed basically at the beginning. So, and then because of dynamic friction, they fall in and start to spiral into the center and merge together. So these galaxies, because these globular clusters, because they were basically formed at the beginning, they have a very simple old stellar population and are then decoupled from the formation history of the galaxy. So we have some evidence of these two scenarios. For example, here that was from a MUSE program to get MUSE is an IFU, so you can measure spectra in a huge field of view. It has one arc-minute field of view. So you can measure basically spectra at different points in a galaxy. For example, at the nuclear star cluster and outside of the nuclear star cluster. So let me zoom in because that's not really helpful. So there are two cases we see. On the left here, you see the radial profile on the x-axis and the metallicity on the y-axis. The dots, there are basically measured points along the galaxy, and the cross is the nuclear star cluster. So what you see is that the nuclear star cluster follows the profile of the metallicity of the galaxy. So this is evidence for the creation, the in situ creation of this nuclear star cluster. On the right, however, you see that the nuclear star cluster is much more metal poor than the rest of the galaxy. So probably has been decoupled from the star formation rate of the galaxy. So this is evidence for the migration scenario. However, this has not yet been, okay. So as I was saying, there are these two scenarios, and we see a trend in the mass of the host. So if a galaxy has stellar mass higher than 10 to the power of 9, what we see is that this in situ formation channel is dominating. And if we have smaller a smaller stellar mass, so in the dwarf galaxy regime, we see that the migration scenario is dominating. I'm working on dwarf galaxies, and I'm a part of this MATLAS collaboration, which has been now doing observations for over 10 years. And we observed with the MegaChem on Mauna Kea over 200 elliptical galaxies to a very deep surface brightness. And in this survey, we found over 2,000 dwarf galaxies. So this is an absolute amazing data set to actually study this. So to study dwarf galaxies in different environments. We got a Hubble Space Telescope time for 79 of these dwarf galaxies, and 41 of them have actually nuclear star clusters. So that's a really cool data set to study the formation path of these nuclear star clusters. So far, the only evidence for these two scenarios is basically through the spectroscopy, but we have not yet measured or seen any sign of migration in dwarf galaxies, like direct imaging of that. So here is just a snapshot of these dwarf galaxies, and what is really nice about these dwarf galaxies, they are of low surface brightness. So while you see in the center, this nuclear star cluster is super bright, everything around it is really shallow. That's super cool, because then we can see features surrounding the nuclear star cluster. In high surface brightness galaxies, you can't, because they are just too bright. But in dwarf galaxies, you can. So we were thinking, okay, what signal would we actually see for this dwarf galaxy, so in the formation of the nuclear star cluster in dwarf galaxies, and for that we set up, and with we, I mean, not I, but Rory Smith. So I'm an observer, I'm not a simulator. So here are the properties, which I think could be interest of you, but please don't ask me more, because I can't answer that. So we set up simulations of nuclear star clusters, so migration of nuclear star clusters, of globular clusters to form a nuclear star cluster. And I hope this works. I usually don't use videos. So here's a video. Yes, perfect. Wow, it has music. Didn't know that. So you see, when you merge, let's say, two globular clusters or a globular cluster with a nuclear star cluster, you see tidal features. So quite unsurprisingly, you have two stellar compact objects, and they basically produce tidal features. So here we set up different types of mergers. We have globular cluster mergers. We have nuclear star cluster mergers with different mass ratios, and nuclear star cluster mergers. And in all of these different setups, what you see is that, you get some tidal features, but they are very short-lived. So starting from 100 mega years, which is short-lived in astronomical terms, basically the features vanish. So it's unsurprising that this hasn't been found yet, because basically that's gone in a blink. So you need to be really fortunate to actually observe these. But because we had quite the large sample of nuclear star clusters, we were actually super lucky to serendipitously, difficult word, to actually find these in the act. So if you look here, that's a nuclear star cluster. You see some tidal features here. There's some tidal features going on, and I think this one is the most beautiful, which you don't see here. If you squeeze your eyes, please trust me, there's a stream going on from here, this nuclear star cluster, all the way down, with exactly these properties as we have simulated. So this, I would say, is one of the first evidences that these nuclear star clusters form, in dwarf galaxies at least, through direct evidence that they form from mergers of globular clusters. And okay, I stop here. Perfect timing, I'm Swiss, so 10 minutes it is.
Oliver, we can tell that you're in Switzerland because you respect time. With respect to these nuclear star clusters, you might expect that the in situ formation will lead also to the formation of a central supermassive black hole, because you have gas making those stars, and the gas can also feed a supermassive black hole.
Yes.
Whereas globular clusters, you know, we have limits on the black hole at their center. You won't get much black hole growth out of that.
Yes.
Is there indeed a difference in the black hole population between the two scenarios you mentioned?
I think there's a little bit of a problem as well, that it's not as simple as that, what I said before. There's also, it could be that you have wet mergers, which make it a little bit more complicated. That's basically when you form some clusters with a lot of gas, which still brings the gas towards the center. So with that sense, I remember we actually had a paper on it, on a dwarf galaxy nuclear star cluster, where we found a black hole in there from the dynamics. And now I think, if I remember correctly, also the metallicity was lower than the surrounding stellar population, so points towards the migration scenario. But yeah, it could be that we have this, basically this, are in this intermediate range here where things can get messy. So yeah, I don't think it's that clear if you have a black hole that it is one scenario versus the other, but it's a really good point. But you would need dynamics, which is really hard to get, because with spectroscopy is.
Any questions, comments, please? Just.
Yeah, that was a great talk. Have you found any environmental dependence for these? So, for example, a field dwarf galaxy versus a dwarf galaxy that is clearly a satellite of a brighter galaxy. Is there a difference in their population of migration or in situ nuclear star clusters?
So we have a huge population. We have, a huge population. It's these dwarf galaxies. If you look at them, they are basically all dwarf ellipticals. I don't see any dwarf irregular here. So, because we were a targeted survey around giant elliptical galaxies, we are basically in the quenched environment. So, even though it is different galaxies in different environments, it's still all quenched dwarf galaxies. So, in that sense, I don't think we can make any statistics on the environment. But it would be very cool to actually look at it. But the problem with dwarf irregulars, so in the field, they will be high surface brightness, so it will be super difficult to actually see the features.
Thank you.
Any other question? If not, let's thank Oliver again.
So put it here.
So hello everyone. I would like to talk about or introduce today the MSA 3D survey, which is a James Webb program PI'd by Tucker Jones, who's here today as well, using the multi-object spectrograph on board of James Webb in the slit stepping strategy in order to obtain the integral field spectroscopy of redshift 1 galaxies. However, before going into the first survey results, I would like to lay some groundwork as to the motivation for gathering this data in the first place. So, as we know from the nearby universe, galaxies can be classified according to the Hubble sequence into star-forming disks and passive spheroids. And thanks to extensive imaging surveys that have proven valuable in establishing the presence of disk-like structures all the way out to redshifts higher than 3. However, it is only with resolved integral field spectroscopy that we can unambiguously establish the presence of rotating disks out to, or at least at any cosmic time at all. And of these look-back times, redshift 1 is thought to be the period of significant transformation in galaxy formation history. In that sense, as we've seen from Madao plot here, the galaxies are growing in mass significantly around this epoch of redshift 1, and at the same time, this is also the period of significant obscuration where star formation is significantly obscured by dust. More than 80% of it is obscured. However, also there is a lot of structural transformation happening as well, where Wisniewski et al. 2019 has shown that around redshift 1, thin disks are starting to emerge. And so in this structural transformation and mass growth is closely linked to star formation and self-regulating processes as well. So it is necessary to in a spatially resolved sense, map dust-corrected star formation rates across a large sample of galaxies at this epoch of significant transformation to probe the progression of structural assembly and the transition into ordered thin disks. And this is possible with James Webb's near-spec instrument, which offers excellent spatial and spectral resolution to actually measure the velocity dispersions characteristic of thin disks. And one can do so in a very time-efficient way by using the multi-object observing mode, which is traditionally used to observe large samples. But if you employ the slit-stepping strategy, you can actually build the IFUs. What I'm showing here is cut out from a larger field where we're targeting all of the galaxies in our sample. And you can see the single slit overlaid over all of these sources, example of which is zoomed in here. And the single slit that is being projected onto the object can be mapped across the entire galaxy in a slit-stepping pattern in order to map the IFU. And what I'm showing here is the pattern that we have employed to get at the end to the IFU cube. So these 5 rectangles are the slits that we are seeing here, stepping in 9 steps in the dispersion direction and 7 steps in the cross dispersion direction, totaling 63 pointings and mapping the cube across the green shaded region in a uniform coverage in these 2 arc seconds, which is shown as the area here marked with the white rectangle. With this strategy, we are gathering or observing high-resolution kiloparsec scale integral field spectroscopy of 43 main sequence galaxies. And all of this is done in about 20 hours of integration time, with which we are significantly gaining efficiency compared to the near-spec IFU, with which we would require more than 350 hours to obtain the data of the same quality. I'm showing here the star formation rate, stellar mass plane of the entire sample, of which I'm singling out a single source here marked with a dark or filled in hexagon. I'm going to refer to this object multiple times throughout this talk, but I'm showing here the cutout from the cube that we actually gather with this strategy, where you can see a prominent spiral structure and also singling out a single spaxel marked with the rectangular, with the square here. You can see the single spaxel 1D spectra. So we are observing rest frame optical emission lines with which we can not only characterize the kinematics of these galaxies, but also characterize the metallicities, attenuation properties, AGN presence, and so on. So this is offering, this method is offering high resolution kiloparsec scale across the epoch of modern thin disk emergence. I like to show this plot because it is showing the quality of the rest frame optical emission lines that we can get for individual galaxies at redshift 1 and how the quality compares to redshift 0 surveys like MANGA. So the galaxy that we have seen in the previous slides is of the mass 10 to the 10.5. So it's on a more massive end. But I'm showing here a MANGA galaxy of a similar mass and similar morphology. So as you can see, prominent spiral structure here, very well fit by a rotating disk. And you can clearly see trends in the attenuation properties as a function of, like, all the way to the outskirts of the galaxy, as well as the metallicity trends. If you want to see more about this particular galaxy, I can refer you to this survey overview paper where we're also looking at test case study galaxy being this one. So mapping the star formation activity across different regions of galaxies not only offers an insight into how mass is being assembled, but also what is the role of different regulatory processes within the galaxy, but also merger or other influencers on the formation of the structure. And it is also a very valuable test for inside-out growth. So it has been strongly suggested, for example, by Nelson et al. 2016, that galaxies are experiencing an inside-out growth. And we can test for this with the sample looking at individual galaxies. And just looking at this one specific galaxy out of the sample of 43, we are not seeing, so based on the H alpha and also comparing it to the stellar continuum that's shown here in black, we're not seeing a signature of an inside-out growth. As a matter of the fact, the new mass that's being added at all radii is actually following the distribution of the stellar continuum at all radii. So but this is just an isolated case, and this is not the case for the rest of the sample. We need to look at the rest of them. The point is that with this survey, we can characterize the attenuation-corrected star formation activity and also identify processes that are driving this activity, which are inevitably going to reflect in the surface brightness profiles like compaction or inside-out quenching. To characterize the dust attenuation at redshift 1, we can look at the ratios of hydrogen recombination lines, the fixed ratio of which indicates the level of the attenuation by dust that is in the system. This is the number of galaxies, so 25 of them, for which we have both measurements and for which we can measure the attenuation. In terms of global attenuation properties, so integrated light across a larger radius in a galaxy, so effective radius here in this case, we can look at the global attenuation in these individual sources, and we're seeing a increasing trend with mass. So more massive galaxies are showing more attenuation, which is in agreement with the results from redshift 2 survey like MOSDEF. And on its own, this result can just suggest that there is not a significant evolution in dust properties from redshift 1 to redshift 2. But these individual galaxies probably have, and as we'll see from the next slide, have very different attenuation profiles, which if they're averaged out, this is washed out and will show such a trend. However, you're seeing, I'm isolating two galaxies at a very similar mass, very close in star formation rates that have significantly different attenuation profiles. One of them is showing in a radially decreasing attenuation, so centrally concentrated attenuation and decreasing as a function of the radius. I would just like to finish this slide. The other one is showing the inverted gradient, basically showing that the attenuation increases as a function or flattens out as a function of the radius. And this is just showing us the variation in individual evolutionary paths in these galaxies. And when in terms of the corrected profiles of the emission, we can see still the exponentially decreasing surface brightness profiles. The individual maps of these galaxies, of the observed H alpha fluxes and the corrected star formation rates, are revealing sites of ongoing star formation which would not be shown if we wouldn't correct for these, for the presence of dust, and are showing us valuable insight into sites of star formation across different radii. Thank you.
So Ivana, it was the numbers you mentioned for the star formation rate, and given the redshift, you know, the age of the universe at that redshift, that doesn't allow you to build up as many stars as you see in the galaxy. So presumably they were starburst initially, and now they're in a different state, right? Because what I'm saying is you take the star formation rate, multiply by the age of the universe, you don't get the mass of stars that you see, right?
Are you referring to this plot right here?
Well, this
In
doesn't
terms of
tell me.
requirement?
No, you had some information about the star formation rate.
Yes.
And given the redshift, I'm saying it's not enough to give you the mass in stars that you mentioned as well.
Yes, but with the mapping the star formation activity across the galaxy, we can see the rate at which stars are being formed in this very moment.
Exactly. What I'm saying is it must have been higher before, because
Yes, they have evolved somehow to get to this point, but by tracing star formation activity in this very moment, because not all of these galaxies have settled at this point. They're in the process of settling, right? If they have settled, we would have already been seeing kinematically that they're, because we can go down to velocity dispersions of what this galaxy has a velocity dispersion of about 30-something kilometers per second. So we can measure velocity dispersions characteristic of thin disks. If we're seeing that the entire sample has settled by now, which it hasn't, but if we're seeing that, then all of them would have similar velocity dispersions. We're seeing higher velocity dispersion measurements, meaning that they're in the process of, settling. And as they are in that process of settling, we can look at them at different stages of settling and see how the star formation activity and different signatures of different regulatory processes inform us of how this transition is happening towards the disk, settled disk.
Exactly. No, I mean, I was exactly referring to the panel on the left here, which shows the star formation rate and the stellar mass, and the ratio between them is actually bigger than the age of the universe at
Yeah.
redshift 1. Okay.
Thank you.
Any other comments? Yes.
Yeah. Have you tried to do the same exercise with the profiles of extinction on local galaxies using manga?
Not yet, but this is a very interesting experiment to be done. But technically, we can do this and look at the difference in properties. The only thing that I'm aware of is the existence of. I haven't added the SDSS data to this plot right here. But yes, we can do this.
Also check Khalifa surveys.
Yeah.
The IFU survey of very nearby galaxies, because they cover like at unprecedented detail.
Yeah. Okay. Thank you.
Okay. Yes, go ahead.
Thank you, very nice talk. I would like to ask a technical question. So what is the spatial resolution that you are reaching with the current line map? Is that still limited by the sharper size, 0.2, 0.5?
So we're using the highest resolution grading and filter combination on board of NearSpec, and the resolution is RF 2700.
I'm asking the spatial.
Sorry, spatial resolution. The spatial resolution element is 0.1 by 0.2 arc seconds. The IFU would be square 0.1 arc second. So we're losing an element there because in the dispersion direction, the element is 0.2 arc seconds. But even with that, still at this look-back time, we're resolving a kiloparsec scale structure.
Very nice. Let's thank Ivana again.
You're able to see. Yeah, put it like this. Yep, I guess you can hear me well, right?
Yeah, perfect. So thank you so much for having me here again. Finally, I can get to talk to you about some of the new results we have been working on since the late August from last year. So basically, what I'm going to show you today are the new results from the DESI collaboration based on the Baryon Acoustic Oscillation measurements and what we are finding on the side of cosmology. So let me put a little bit here the timer because there are plenty of things to say, but very, very less time. So before jumping to everything, I have to tell you a little bit about what DESI is. Basically, so I can go quick, DESI is an instrument that does a survey in the sky and measures the redshift of the galaxies based on spectroscopy. So basically, DESI, as you can see here, has a 3.8 primary mirror that basically takes the light, reflects it up, and then it is collected by an army of 5,000 robotic fibers that basically is able to move around to get the light from different galaxies. And then this light is passed to spectrographs that basically analyze the spectra. But the nice thing about DESI is that it's an instrument that comes from the experience of many, many years from surveys like SDSS. And it is optimized to measure as many redshift as possible in very less amount of time. So DESI, what it wants to do is to build a map of the universe by knowing very well the angular position of the galaxies as well as the redshift. The DESI target acceleration program is based on 4 different tracers. So at very low redshift, we have simply bright galaxies. Later on, as we continue to move farther and farther in redshift, we have luminous red galaxies, which are these LRG here, and these are basically red elliptical galaxies. And as we keep going, we'll have other objects like these blue galaxies with a star formation that we call emission-like galaxies, and at the end, the farthest objects from us that are the quasars. Right now, we have collected for this Baryon acoustic oscillation analysis that I'm going to talk to you a little bit, around more than 14 million galaxies. If you compare this with our previous data release, what we used for BAO at the time was around 6 million galaxies. So we have got more than double in the number of galaxies, plus Lyman alpha force spectra that also help us to know about the structure formation of the universe. So the takeaway message from this slide is basically that DESI provides us with a 3D map of the universe covering around 30% of the sky fraction. So what we can do with this map and what is the idea behind everything, and our data set is basically this, is to measure a signal that comes from the very early universe, which are the Baryon acoustic oscillations. So to understand this, you have to go back with me around 400,000 years before the Big Bang, a little bit less than that, in which you had this primordial plasma, which was very hot and dense. So this primordial plasma was made of various components. So you have the dark matter particles that basically just interact gravitationally and form overdensities. And then we have the baryons that try to follow these overdensities and collapse due to gravitation. But then there is also the photons in this plasma in which the mean free path of the photons is very short, and then they were always going to be doing a scattering with the baryons. This is going to induce an oscillation pattern in the plasma that is going to propagate as sound waves in the plasma. However, as the universe cools down and it is expanding, what you're going to have is that later on the electrons are going to start to combine with the protons to form neutral hydrogen, and then the scattering rate of the photons is going to drop. So what will happen at that time is that we'll have decoupling, and all these different oscillation modes are going to stall. But then there is one particular oscillation mode that is very relevant to BAO, which is the wave or the sound wave or the oscillation that goes all the way from the Big Bang till the time of recombination. This one is very important because it leaves an imprint or a minor excess of baryons common in various regions of the universe. This is going to define a ruler, which is very nice because these characteristic scales, once you have the decoupling, basically you can, it's like a ruler that you can propagate or project along the redshift. And then once you let the system evolve, this characteristic scale is going to have an excess of galaxies. How do we measure this? Basically, we count pairs of galaxies and form a correlation function. So what you will see is that once you start building this histogram that tells you the excess of find a pair of galaxies at a given distance, you will find a peak at very small scales, and in principle, this function should decay, but then you will find this scale that gives you this excess of baryons. And that is actually what we are trying to measure with these statistics of many, many galaxies mapped by DESI. So what we are measuring at the end of the day are these parameters, alpha iso and alpha IP, which tells you the isotropic scale of these shells, and AP, the anisotropic warping in these shells. So the nice thing about this is that, as I mentioned, it measures the redshift of many galaxies across various redshifts. And so what you can be doing is that you are probing the structure across different redshifts billions of years later, given this signal that happened at recombination. So ultimately, what we are gathering are measurements of this BEO signal for various DESI tracers in various redshift bins. There is also a very high redshift data point coming from Lyman Alpha 4S emission, but you can hear more about it in 2 weeks when Andrew von Rivera is coming. Basically, what we have is this set of BEO measurements. What we measure are ratios of distances, the cosmical distance divided by this ruler. But then it is very nice because once you combine all these measurements and translate these ones into cosmological parameters, you will see that as we go farther and farther in redshift, these contours are starting to tilt given the general direction of the measurements. So this plot is very nice because it kind of illustrates the complementarity of the different BEO measurements. So for example, here you have BGS, and then as we keep going farther and farther in redshift, and we end up with Lyman alpha, which is this purple contour. And then once you combine all these measurements, you will get a very shrink measurement on omega m, and also the combination H naught times RD, which is this ruler. So the nice thing is not just to look at DESI by itself, but how DESI looks compared to other cosmological props that we have in the market. In particular, the two that are very relevant to us is one is CMB, and the other are supernova measurements that can inform us about the matter content of the universe. So one of the implications we are seeing is like we start seeing these slight discrepancies at the level of the cosmology that we measure. For example, if you look at this orange peak, you will find that Planck likes an omega matter value around 0.315, but then DESI is slightly predicting a lower value for omega m. On the contrary, if you look at the supernovas, you will see that they like a much higher value for omega m, and even though depending on which supernova data set you pick, they kind of, all of them, they are pointing towards that direction. But the key thing to observe here is like, if you look, you can start seeing some tensions. For example, you have the DESI survey and the DES Wi-Fi supernova, and you will see that there is already some tension around 3 sigma going on here. If you look at the cosmological constraints on this plane, which is what DESI measures, you can see that at least with respect to Planck, as we get more data and we jump from DESI DR1 to DESI DR2, these kind of discrepancies are still present, but also getting a little bit tighter. You can ask me about what happens if you include ACT. I don't have it here on the slides because we want to write a paper about it, but I'm happy to ask you. Ultimately, what this makes is like each of these data sets, it can be fit very well with lambda CDM. Actually, lambda CDM does very good at fitting each individual data set, especially CMB. However, the issue that we are observing is like these different probes, even though that each of them, they like lambda CDM, they cannot agree on which lambda CDM they like. So later on, what this propagates further is into the fact that when you extend this lambda CDM model to some other extensions, they find regions in the parameter space as you open it up in which they are actually get to be consistent. And so there are many ways to do extensions, but however, you can look at the name of DESI, right? It's dark energy, so we need to go and check for deviations away from the cosmical constant. How we do it is by this phenomenological parameterization that basically tells us the equation of a state today, and then we allow for a redshift evolution. What we have been finding is like with more data, this evidence keeps just getting stronger and stronger. And so you can see here that already without using supernova, just DESI plus CMB, we are seeing a 3 sigma tension in this case with respect to lambda CDM. And if we include the different supernovas, this tension can change. However, the constraints, they all end up falling in this region. In particularly, the largest tension that we find is already surpassing the 4 sigma threshold when we use the DS Wi-Fi supernova data. We did many tests. So for example, not to try to rely on this CPL parameterization, and we use other techniques. However, even if we use binning, Gaussian processes, we are still kind of finding a similar signal. And even if we do data cuts and we replace Planck with DS 3 times 2 point and so on, we kind of still find the same sort of conclusions. Ultimately, just to leave you with that, I will say that DESI can also constrain the neutrino mass parameter. And you can see that already we're seeing a lot of troubles in cosmology, but this constraint on the neutrino mass is going far below, it's starting to go below the inverted hierarchy. However, if we include this, we allow for a more complex background, we are going to see that we allow for a wider range of masses, and also, fortunately, the peak kind of start to shift towards positive regions. Of course, thanks to the DESI sponsors, and I will just leave you with this concluding slide, but happy to take questions or chat afterwards. I know people may have many. Yeah, thank you.
I know that observers do not like to listen to theories because you just observe, collect data. But on the other hand, you showed us a plot of supernova versus DESI, and it's clear that there must be systematics which are more likely to be in the side of the supernova because it's not, we don't fully understand the physics of supernova.
You said it.
But my point is it makes no sense to combine 2 data sets that disagree so much on omega matter and say, oh, now lambda CDM is not correct, because I would argue supernova are not correct, right? And you know, W of less than -1 is a very crazy thing, theoretically speaking. You know,
Yeah.
so I would say limit W to -1, and let's see which data set is reliable.
Yes, that is a very good observation. So basically, I think I have the plot here somewhere. The issue is like if you, I mean, of course, we are aware that we have these discrepancies in lambda CDM. That's why we don't combine DESI and supernova in lambda CDM itself. However, we are forced to look for extensions as well. And so when we look for this dynamical dark energy, which is based on this CPL parameterization, that it's not, people say a Taylor series, but in principle that parameterization matches the observable from actual physical theories. The only problem here is like it's going to phantom, right? But as you move, or you look at this plot in that more generalized background, what you will see is like the DESI omega matter shifts higher, and then there is no disagreement. So that's why we're kind of allowed to combine it on that model.
But is your gut feeling that really the dark energy is behaving with W less than -1?
It's difficult. When I talk to theories people, well, I guess Daniel wants to say something, but when I talk with theories people, I think the issue is like if you want to really force on that, you have to get more complicated models, like even more scalar and so on. So yeah, Daniel, you can have.
Yeah, actually, so I mean, it could be that one of the data sets is wrong, but I was actually pretty impressed by a paper last week that came out of the researchers in Penn that point out that they have a model where dark matter and dark energy are coupled as a dark baryon, dark axion combination. And then you get phantom, because the combination of dark matter and dark energy together are not phantom. It's only when you declare that CDM is in one part and dark energy is another part that you complain that dark energy is phantom. If you think of them as a coupled system, the densities are continuing to decrease as the universe expands, and it is not enough phantom regime.
But just to clarify, dark matter clumps in galaxies, right? Dark energy does not clump.
Sure.
So what is exactly going on in terms of the coupling? I don't understand.
Like this dark radiation.
You have a medium that is completely uniform, and then another
Look
medium.
at the paper, but
I see.
yeah,
It's possible.
you could have a coupling between these 2 things, and one of them has a high pressure,
And it doesn't change rotation curves.
No.
Okay. Okay.
Yeah, no, and just to finish on that point, I will say like, yeah, I think it's a good time for the theories to start kind of getting these kind of models as we get more data. The nice thing is like people are kind of putting the eye on supernova, and we'll have CTF soon, and hopefully it's going to shed some light on what's going on as well, because we're very sensitive to the low redshift data from supernovas. Sorry.
Yeah.
So by the end of DESI, you should have 50 or 60 million galaxies, something like this?
I think it should be 40 million galaxies, and then we'll have a DESI extension. However, we don't use all the galaxies we have in the analysis.
So what should I expect to happen to the blue curve? Should it squeeze by a factor of √3 in width, and it'll either move towards the CMB or stay where it is, and you can make a strong claim without the supernovae, or what do you think?
Yeah, so, and I think, of course, Daniel can complement, but what I have seen in terms of forecast is like with the DESI extension, people expect like if the things stay where they are and you just shrink the error bars by means of forecast, principle what we expect is like we can get a 4 sigma deviation without supernova, just DESI and CMB.
I agree.
Yeah.
So that's within a year?
No, with how long is going to be with the extension?
So, okay, well, that's not a long time compared to the Hubble time. Any other comment? Well, this is really, I mean, cosmology became very boring. And this is a shot in the arm because it's really difficult to explain theoretically. So it will, I'm sure there will be hundreds of theoretical papers.
Yeah. I think there should be.
Any questions? Final questions?
Is there a job tension between the neutrino mass band with oscillation, neutrino oscillation experiments?
Well, actually, neutrino masses could be negative, right? That's the favorite.
We also test that. Yeah.
So how much is the tension now with the lower band coming from neutrino oscillation?
Don't remember exactly the number for that one. I know you have.
It's consistent.
Yeah, I mean.
It's still consistent.
It's still consistent, but I mean.
What about
negative,
negative neutrino masses? That doesn't make any sense, right? I mean, would observers claim that we have negative neutrino masses?
But you don't have to have that if you have W0 WA.
Okay.
So
Yeah, so
that strong limit's only for lambda CDF.
So at least this was kind of a relief, I would say, because I was also getting this neutrino masses thing, and some people even really claim that we are not even measuring the mass itself, but an effective parameter. But then a relief could be like if you go to this marginal background, you will find cases in which the peak actually goes to the positive region. So that's an okay thing for now. Not sure how it will behave later.
Yeah, so that it's more sensible to throw all the disagreement into the dark energy than negative neutrino masses.
Yes, no worries, thanks.
Yeah. Okay. With that, let's thank Cristhian and.